Good afternoon, everybody. I am Priyadarshini, AP Department of Mathematics, Sri Shanmugha College of Engineering and Technology, Salem. I am going to discuss about the topic is queuing theory. So the definition of queuing theory is, the first one is the basic phenomenon of queuing arises whenever a shared facility needs to be accessed for service by a large number of jobs or customers. The second one is, we study the phenomena of standing, waiting and serving, and we call this study queuing theory. Any system in which arrival's place demands upon a finite capacity resource may be termed a queuing system. The third one is the study of the waiting times, lengths and other properties of queues. The next one is applications of queuing theory. So first application is telecommunication, and the second one is determining the sequence of computer operations. Third one, prediction computer performance. Fourth one of the key modeling techniques for computer system or networks in general. For example, vast literature on queuing theory, nicely suited for network analysis. And the fifth application is traffic control. Sixth one is airport traffic, airline ticket sales. Seventh one is layout manufacturing system. Eighth one, health services, for example, control of hospital bed assignments. The next one, queuing theory for studying networks. View network as collections of queues, first in first out data structures. And the second one, queuing theory provides probabilistic analysis of these queues. For example, average length, average waiting time, probability queue is at a certain length, probability a packet will be lost. So next I represent the diagram for queuing model system. The uses of queuing model is describe the behavior of queuing system, evaluate system performance. So next also use this diagram. So next one, characteristics of queuing system, candle notation 1/2/3/4/5/6. 1 is represented by arrival distribution, 2 is represented by service distribution, 3 is represented by number of servers, 4 is represented by total storage including server, infinite if not satisfied. Fifth is represented by population size, infinite if not specified. Six is represented by service discipline, first come first serve or first in first out. Next one is distributions of queuing theory. M stands for Markovian or Poisson, implying exponential distribution for service times or inter-arrival times. D represented by deterministic, for example fixed constant. Ek represented by Erlang with parameter k. Hk represented by hyper exponential with parameter k. G is represented by general or anything. So next topic is Poisson process and exponential distribution. We represented inter-arrival time t in a Poisson process follows exponential distribution with parameter lambda. So probability of t equal to lambda into e power minus lambda of t. This is the formula for Poisson process, and E of t means mean of t, which is equal to 1 divided by lambda. So next we use this diagram. Next examples of model 1, M/M/1, Poisson arrivals and exponential service, 1 server, infinite capacity and population, first come first serve or first in first out. The simplest realistic queue. The next model is M/M/m/m. Same but M servers, M storage including servers. Example telephone. The next one is analysis of M/M/1 queue. So lambda means arrival rate of customers, mu means service rate of the servers, L represented by average number in queuing system, LQ represented by average number in the queue approximately equal to 1, W represented by average waiting time in whole system, WQ represented by average waiting time in the queue is represented by 1 by mu. Next, view the diagram in model 1. The next one is derivation for model 1. The value of rho is lambda divided by mu since all the probabilities sum to equal to 1. Summation k equal to 0 to infinity rho power k into p naught, which is equal to 1. The next one is we find the formula for W, WQ and LQ. First we define the formula rho equal to lambda divided by mu. Next the formula for LQ is rho square divided by 1 minus rho. The formula for L is rho divided by 1 minus rho. The formula for WQ is rho divided by mu into 1 minus rho. The formula for W is 1 divided by mu into 1 minus rho. The next one is probability for n. Pn equal to 1 minus rho into rho power n. For stability, mean arrival rate must be less than mean service rate. Utility factor rho equal to lambda by mu, which is less than 1. Next, we represent the diagram for response time with arrivals. So next one is example for model 1. On a network router, measurements show the packets arrive at a mean rate of 125 packets per second. The router takes about 2 milliseconds to forward a packet. Assuming an m/m/1 model, so next to find out what is the probability of buffer overflow if the router had only 13 buffers. The next question is how many buffers are needed to keep packet loss below 1 packet per million. So given data are lambda equal to 125 packets per second, service rate mu equal to 1 divided by 0.002, which is equal to 500 packets per second. Router utilization rho equal to lambda divided by mu, which is equal to 0.25. Probability of n packets in the router, which is equal to, the formula is 1 minus rho into rho power n. Substitute rho value 0.75 into 0.25 the whole power n. Next we find out mean number of packets in router, which is equal to, the formula is rho divided by 1 minus rho, which is equal to, the rho value is 0.25 divided by 1 minus 0.75, which is equal to 0.33. Next we find probability of buffer overflow, which is equal to P of more than 13 packets in router, which is equal to rho power 13. Rho value is 0.25 the whole power 13, which is equal to 1.49 into 10 power minus 8, which is equal to 15 packets per billion packets. To limit the probability of loss to less than 10 power minus 6. So next one is rho power n less than or equal to 10 power minus 6. N greater than log of 10 power minus 6 divided by log of 0.25, which is equal to 9.96. This is the answer of this problem. Thank you.